When light traveling through some medium, for example air, hits the boundary to some other medium, say glass, some fraction of it is reflected back into the first medium, while the rest is refracted as it enters the second medium, meaning the direction in which the light is traveling changes. This change in direction is governed by Snell's law of refraction after Willebrord-Snellius, and it relates the angle of incidence to the angle of refraction and the refractive indices of the media in question. If you're like me, you probably got introduced to Snell's law while taking high school physics classes. But at least in my case, I don't think I was ever shown where this equation actually comes from. Since then, however, I have learned that it is possible to derive it in a number of different ways. In this video, I intend to do it by starting from the fundamental postulates of ray optics, which is the oldest and simplest theory of light. Then, in the next video, I will show how this scalar form of Snell's law can be generalized into a vector form, which can be used to create accurate simulations of optical systems in 3 dimensions. So, first of all, let's establish some postulates. These are fundamental assumptions we make about the behavior of light. We can then apply these postulates in different situations and see what laws and principles we can discover, similarly to how axioms are used in math. The first postulate says that light propagates through space in the form of rays. Now I remember being confused by this at first, since the mathematical definition of a ray is a straight line which begins at some point and then extends to infinity. But in this context, light having a ray form simply means that it follows some continuous path through space. The second postulate says that an optical medium is characterized by a refractive index n, defined as the ratio between the speed of light in free space and the speed of light in the medium, and that this ratio is greater than or equal to 1. Using more advanced theories of light, it can be shown that this is not always true, but for this video we can safely stick to this assumption. The third postulate declares that light travels between 2 points along the path of least time. This is not strictly true either, as the time needs only be stationary with respect to variations of the path. But this definition is often used for simplicity and is called Fermat's principle, after Pierre de Fermat, who was the first to propose it. From these fundamental postulates, we can already derive some additional information about the behavior of light. For simplicity, let's assume that we are dealing with homogeneous media, meaning they have constant refractive indices. One thing we can say is that the time it takes for light to propagate the distance d is given by the distance divided by the speed of light in the medium, which can also be written in terms of the refractive index. It is then apparent that the time t is proportional to this quantity n times d, which I'll be calling capital D. It is known as the optical path length. Since the refractive index is a unitless quantity, the optical path length has units of length, and is simply a scaled distance. I like to think of it as the distance the light would have traveled in free space in the same amount of time t. And as the time t is directly proportional to the optical path length, finding the path of least time is equivalent to finding the shortest optical path length. Also, since the shortest path between 2 points in Euclidean space is a straight line between them, and the refractive index is constant, it follows that the shortest optical path length is along a straight line between the points. And as such, in a homogeneous medium, light travels along straight lines. This is called Hero's principle, after Hero of Alexandria, who formulated it as early as 2 millennia ago. The optical path length can also be generalized to inhomogeneous media, where the refractive index varies with position, such as it does in graded index fibers. But for this video, let's restrict ourselves to constant refractive indices. Now that we have established our postulates, let's see what the natural consequences are when we examine how light transition between two homogeneous optical media having refractive indices n1 and n2. Let's say that we want to find the path light takes between two fixed points, the first located in the first medium, let's call it A, and the second point B located in the second medium. Now, we know from Hero's principle that light travels along straight lines inside each medium, so the path the light takes from A to B should look something like this. But Hero's principle does not tell us where the light intersects the boundary between the two media. If we want to know the actual path, we have to apply Fermat's principle directly, which essentially involves minimizing the optical path length. So if we call these two distances d1 and d2, the total optical path length is then given by this expression. Now, there are several ways to minimize this quantity. You could use the Pythagorean theorem and end up with the Snell's law in terms of distances if you want. But what I'm going to do is to draw a normal line which is perpendicular to the surface at the point of intersection, and then define these two angles, call them θ1 and θ2. These are of course the angles of incidence and refraction, respectively. The idea is now to express the optical path length in terms of these angles. For this purpose, I'm going to draw these horizontal distances. Let's call them x1 and x2. These are fixed, since our points A and B are fixed. We can now see that the cosine of θ1 is x1 over d1, so d1 is then x1 over the cosine of θ1, or x1 times the secant of θ1. So we can insert this expression for d1 in our equation for the optical path length. We can then use a very similar argument to express d2 in terms of θ2, and we thereby have our function to minimize. In order to do this, I want to use the method of Lagrangian multipliers, which is a very common technique. If you're unfamiliar with it, I recommend checking out Khan Academy's section on it. I went there myself in preparation for this video to refresh my memory on how and why this method actually works. But I won't go into detail about it here, since I feel that it would derail the video a bit. Basically, what we're missing is some constraint on the variables θ1 and θ2, and in order to find that, I'm going to draw out these vertical distances here and call them y1 and y2. Then I will define this quantity s, which is just their sum, and it has to remain constant as the points A and B are fixed. We can now express s in terms of our angles by noting that the tangent of θ1 is equal to y1 over x1, such that y1 equals x1 times the tangent of θ1, and similarly for y2. So our constraint becomes that this function s must remain constant. In other words, we have now formulated a constrained optimization problem, where we want to minimize the optical path length, subject to the constraint that the vertical distance between the points remains constant. A requirement for any extremum is that the gradients of d and s are parallel, which can be simply written like this, where lambda is a scalar. So, let's work out some partial derivatives. I will just do it quickly here using the rules for differentiating trig functions. The partial of d with respect to θ1 becomes n1 times x1 times the secant of θ1 times the tangent of θ1. The partial of d with respect to θ2 becomes n2 times x2 times the secant of θ2 times the tangent of θ2. The partial of s with respect to θ1 becomes x1 times the squared secant of θ1. The partial of s with respect to θ2 becomes x2 times the squared secant of θ2. These are of course the components of the gradients of d and s. And if we translate our requirement to component form, we end up with these two equations. If we divide the first equation by x1 times the squared secant of θ1, we get this equation, and similarly for the second equation. We can now see that the left-hand sides of both equations are in fact equal, which is obviously equivalent to this familiar equation, the Snell's law we all know and love. But hang on for a moment. How do we know that this in fact corresponds to a minimized optical path length? All we know is that we found a condition for an extremum, which in theory could also be a maximum or some kind of inflection point. Well, I guess there are tests we could apply to prove it rigorously, but I'm going to use an inexact method I feel is more illuminating. I have now plotted our function for the optical path length as a surface for values of θ1 and θ2 in the range 0 to 80 degrees, and some randomly chosen values of the total vertical distance s and the horizontal distances x1 and x2. The refractive indices I used were 1 and 1.6, typical values for air and glass, respectively. On top of the surface, I have also plotted a green curve, along which our constraint is satisfied, and a red curve, along which our condition for an extremum is fulfilled. The single blue point where these three graphs coincide then constitutes our extremum. We can try varying the vertical distance s and see how the extremum behaves. We can also try varying the horizontal distances x1 and x2. The extremum doesn't seem to be a maximum, since the green curve occasionally extends into areas where the path length takes on greater values. We can see this more clearly if we shift our view to a horizontal one. At least to me, it seems that we have indeed found a minimum. But if you don't trust it, by all means, go ahead and try to prove it to yourself. At any rate, we have now seen how Snell's law arises due to a few fundamental assumptions we made about the nature of light. Take note though that when deriving this scalar form, we were always working in 2 dimensions, more specifically in the reference frame of the plane of incidence, which contains both the incident and refracted parts of the ray. In the next video, I'll show how to generalize the scalar form of Snell's law into a vector equation, which applies to any 3-dimensional Cartesian reference frame.